Today I will be going over the first principles of calculus. I will be explaining how they get the formula, just going over to try and make it make sense. So how we start going over this is we need just an XY axis. So you've got your X and your Y, pretty normal stuff. Now let's quickly do a recap of how you find the gradient of a straight line. So I'm sure you know the formula for this. You get your m, you take y2 minus y1 over x2 minus x1. So remember, what is this m? What is this gradient? This gradient, you might have heard the phrase rise over run. It's saying, okay, so let's say over here we've got a point, and over here we've got a point, and we want to know the gradient between these 2 points. So we're saying how much has it risen over how far has it gone to the right. So we call this point point 2 and this point point 1, and then we've got the x1 and we've got the the y1, and we've got the y2 and the x2. So this is what we do to work out the gradient of a straight line. So when we talk about finding the derivative, what we're actually talking about is finding this gradient, this m. But when we're dealing with a derivative, we're going to start talking about what if the line isn't straight, what if the line curves. So when we've got a straight line over here, it's got its gradient, we just sub in these points and we work out our answer, and we get an answer like 2 or like some sort of actual number. So whenever you find the gradient of a straight line, you get an actual number. But let's say this line is no longer straight. Let's say that this line is now a curvy line, and we want to find the gradient of the curvy line. Well, we're going to find a different sort of answer, because the gradient, how steep it is, that's what our gradient is, it changes as the line moves. So we can't just use this formula anymore, because we want to get some sort of answer that's going to be in terms of x. So we want to be able to say, okay, we know the gradient over here, and then we know the gradient over here, and we know the gradient over here, and they're all going to be a bit different. And so we want a whole new function that can tell us what the gradient is at any of these points. And so if you've heard the fancy word derivative, that's what that means. It means the equation that can give us the derivative at any point. We just tell it, okay, we're looking at x is 1, or x is 5, or x is 7, and we can figure out from that what's the gradient. So let's talk about how we're going to figure this out, and we're only going to use what we know. So we're going to do a very similar thing to what we did, getting 2 points. We're going to have we're going to make use of 2 points. So we can call them, so like we did before, where we called it x1 and x2 and y1 and y2. We're going to do something similar, except over here we're going to change the name of y1 and y2. We're going to talk about it in terms of the actual equation. So we're going to say f of x1, and this would be f of x2, right? So we're doing pretty much the same thing. We're just writing y in a different way. We're writing y just to emphasize that we're talking about this function, this curvy line. Okay. So now let's instead, another minor change we're making to how we're writing this is we're going to call this, we're going to figure out what is x2 in terms of x1. So we're going to just call this x1, we're just going to call it x now. And then we're going to say, okay, what is this point? Well, this point is the same as going from the start over there, you get to x, and then you add this bonus space over here. You add this bonus space. So we're going to call this bonus space h. And so this new point is going to be x plus h, because we took the distance of x, we added h to it, so this new point is x plus h. And over here we're going to do we're going to write it in terms of that now. So instead of writing x2 over there, we're going to write f of x plus h. So we've done nothing really complicated here. We've just got 2 points, and the distance between them, the x distance between them, is h. So we've written it in terms of that. Nothing too crazy. But how has that actually helped us to find anything out? Well, so what we're doing here is we're saying, okay, we want to find the equation for x. Okay, and you see I didn't call this x1, I didn't give it a specific number, so that this x, we're going to make an equation where this x can be any x, it doesn't matter. As long as you can add a distance h to it, this will work. So this x could be over there, or it could be over here, or even over there, doesn't really matter. We're just going to pick this point to prove our theorem off of that. Okay, so we want to find out what is the gradient at x. And so the way we find this out is we imagine, what if there was a line, a tangent line to that point. So we're taking a straight line, and we're putting it on that point, and we're saying, so it just barely touches the curve at that point. So what this line means, in other words, is it means, what if our equation at this point, our gradient at this point, our m, what if it just continued exactly like it is, and the gradient didn't change at all? Then it would be the gradient of this line. Okay, so this is the line that we want to find. We want to find the gradient of this line, because then we'll know what's the gradient at that point. And in fact, we want to figure out an equation that will work for any x. So no matter what the slope is, we want to be able to figure out what's the gradient of the line that is tangent to it. And so the way we figured this out is, now we're going to use our x plus h. So we're going to make a line between x and x plus h. So we draw that line now, and so now we've got a line between x and x plus h, a perfectly straight line like that. And is it exactly the same as the blue line? Is it the same as the line we want to find? Not really, no. It's a bit off. Alright. But let's imagine for a minute that this line was actually accurate. How would we get the equation of this line? We would use this equation over here. We would use this equation that we know well, and we would say, okay, the gradient is equal to y2. But what's y2? What are we calling y2 now? We're calling y2 f of x plus h. And what's y1? That's just f of x. And now, what's x2? That's x plus h. And what's x1? That's just x. So, we've got a nice little equation now for finding the equation of the gradient of the line between these 2 points, and we can do a little bit of simplification because we've got x plus h minus x on the bottom. The x's are going to cancel out, and we're gonna just be left with over h. Alright, so we know the equation of the gradient of a line between 2 points. That's not really useful right now, but we are going to get a bit clever, and we are going to say what would happen if we decrease our h. Then we need to focus on the slope of the line. So we're saying this h distance between them, what if it gets smaller? So what if this point 2 comes closer and closer to our point 1? What if it starts moving from where it is and becomes closer and closer and closer to x? What's going to happen there? So as we get closer, we see the gradient is kind of changing as the slope curves down and up and stuff. But as we get closer and closer, you can see it's starting to get a little closer to the blue line. So we're taking h and we're making it a lot smaller. We're making h way, way smaller, and we're moving this point, this orange point, we're moving it closer and closer to our original point. So we are moving our x plus h closer and closer. And the closer we move it, it might wobble up and down a bit depending on the slope of the line, but once we get really, really close, you see it's going to get really, really accurate. It's going to be really, it looks just exactly parallel to that line now, doesn't it? It looks almost exactly the same as the blue line. So the closer and closer we get, as we start getting so very close that h is almost 0, that the distance between the 2 points is absolutely tiny, we're going to find that we get this blue line. We get the gradient of this blue line, because the white line is going to get more and more similar to it. So what we say over here is we're using this equation that we just made, but so we're using our f of x plus h minus f of x over h. We're saying, okay, we're finding the gradient of the white line but we're saying that h is going to get smaller and smaller and smaller, so h is going to approach 0. So this is where we use a limit, and we say, okay, h is coming very, very close to 0. It's the limit of h approaching 0. And we can't make h equal to 0, or then we'd be dividing by 0, and the maths would break, because imagine what if this distance was actually 0. It would be weird. It would sort of break. We wouldn't have any gradient at all if it was actually 0. But as long as h isn't 0, but it's very, very, very close, we're going to get an answer that's pretty accurate to this blue line. So that is the explanation of where we get this equation from, and this equation is your it's your derivative. So this is how you get your derivative, and what we would call this. So if our original equation is f of x, then this is going to be f apostrophe x. So what that means, the derivative of x. And so that's just a fancy way of saying the gradient of this equation at any point. And so I'll make another video going through how we're going to use this equation, but this is how this equation is derived. And I hope that was helpful to you. If you have any questions for me, leave a comment below. If you enjoyed the video, then please like and subscribe. I would really appreciate the support, and it would encourage me to keep making these videos for you. If you really like this and you want to contact me for private tutoring, you can look in the description for a link to my website. But more than anything, thank you for being here, and remember, you're smarter than you think.